We might be ready to start. Hi, everyone. Welcome to our last day of talks, but not last day of fun. I remind you that tomorrow there is a social event going on at the same time. Today we will have 3 talks, each of 35 minutes, and we will start with Brendon Rhoades, who will tell us about Lefschetz theory for exterior algebras and fermionic diagonal coinvariants.
All right. Well, sorry. Well, thank you very much, Angela, and thank you to the organizers for inviting me. It's a great honor to speak here. I hope to be in Sweden and in person someday. The slides, by the way, are on the website. So the work I'm talking about today is joint with Jongwon Kim, who is a grad student at the University of Pennsylvania. So here's the outline. We're going to begin with the classical covariant ring, so that might be a little bit of review. It's come up in a couple of talks already, say Alex Young's. And then we'll talk about some variations on the classical covariant ring, and these variations are going to involve bosons and fermions. These are kind of terms from physics, and I'll explain what they mean in a little bit. And then I'll talk about sort of a new bigraded quotient ring, the fermionic diagonal coinvariants. And then I'll extend from type A to an arbitrary complex reflection group. So of course you are familiar with the ring of symmetric polynomials. We consider the action of the symmetric group on the polynomial ring in variables given by a subscript permutation. And a polynomial in the associated invariant subspace is called symmetric. So I'm teaching Galois theory right now. And the only symmetric polynomial that the students really get to see, unfortunately, is the elementary symmetric polynomial, this guy. Little do they know just how many beautiful symmetric polynomials there are. And this is one thing I think I've taught them at least, Newton's theorem, that says once you've seen these elementary symmetric polynomials, you've seen them all. So this ring of symmetric polynomials is itself a polynomial ring, but now in these generators of elementary symmetric polynomials, this should be advancing. It's not, it doesn't want to advance.
Hold on just a second, try unshare and share one more time. It's funny that it advanced for a little while and then stopped.
Yeah, okay. Okay, let's try sharing now. Okay. Yeah, it's not, oh, wait, so now it doesn't. Okay, there we go. So, so Francois said this in a talk. I'm going to steal this from him, sorry. Symmetric polynomials we know are beautiful and interesting, but the symmetric group finds symmetric polynomials very boring, right? Because when you try to act on a symmetric polynomial, if you're a permutation, nothing happens. So what we have is this interesting representation of the symmetric group acting on a polynomial ring. We have a boring part, and maybe if we kill off the boring part, we're left with something interesting in the end. So the coinvariant ring is the polynomial ring modulo the ideal generated by those symmetric polynomials with vanishing constant term. And we can also think about this as the polynomial ring, thanks to Newton's theorem, modulo the n elementary symmetric polynomials. So what kind of an object is this? Well, this is a graded ring because this is a homogeneous ideal. And this also carries an action of Sn, right? Because Sn is going to stabilize this ideal. So it's a graded Sn algebra. And there are a lot of beautiful results about this. So Chevalier used some Galois theory, the normal basis theorem that I certainly can't teach my students, to prove that Rn as an ungraded module is isomorphic to the regular representation of Sn. So this is a graded refinement of the regular representation. And Lustig and Stanley showed you can understand this thing combinatorially. If I want the graded isomorphism type of this thing, I can write it down as a symmetric function, right? So it's the sum over standard tableau within boxes of, well, your grading tracker to the major index of that tableau. And then you have the Schur function, the stand-in for the irreducible corresponding to the shape of your tableau. And this ring is also important in geometry. So Borel proved, as we saw in Alex Young's talk, that Rn presents the cohomology of the complete flag variety in type A. So it's still not Like it shares, it wants to advance for a little bit, but then it stops. Oh, okay. I think this was happening in Richard's talk too. So, so the people in this community are probably rather familiar with the diagonal coinvariants. So the idea here is that you consider a polynomial ring now in two n variables, so in commuting variables and in more commuting variables. So anyway, we have this diagonal action of the symmetric group on the polynomial ring in two n variables. And Garcia and Haiman said, well, we're going to play the same game. We're going to say this is an interesting representation that has a boring part, namely these invariants. And we'll mod out by the invariants with vanishing constant term. And now what you're going to get is a doubly graded SN module, one grading coming from the x variables, one grading coming from the y variables. And Haiman proved that, well, the vector space dimension this time, it's not in factorial anymore. It's n plus 1 to the n minus 1. N plus 1 to the n minus 1 counts, for example, parking functions. And Haiman also proved that this representation is isomorphic to parking functions times the sign representation as an ungraded module. And as a bigraded module, the bigraded Frobenius image is given by this mysterious thing. You know, you take En and you apply this mysterious Bergeron-Garcia-Nabla operator to it. So this might be a little bit more unfamiliar to you guys. This is an object that I would say rose vastly in prominence over the last couple of years, something called superspace. So what is superspace? Superspace is a rank n unidal C algebra given by tensoring a polynomial ring of rank n with an exterior algebra of rank n. So I'm going to abuse notation a little bit and just write this as if it were a polynomial ring, but the understanding here is that the x variables or y variables or z variables commute, and the theta variables or c variables or any other capital Greek letter Greek variables anti-commute. So this also has a diagonal action of Sn. And we can think about it in a couple of ways. If you're a differential geometer, you'd say, this is the algebra of, well, polynomial valued holomorphic differential forms on Cn. It's kind of tied to differential forms. And if you're in physics, you would say that the commuting variables are bosonic. So somehow they correspond to bosons. So these are particles that can occupy the same position at the same time or be in the same state at the same time, but they're indistinguishable. And the theta variables correspond to fermions. So somehow the relation theta I squared equals 0 is the Pauli exclusion principle. You can never have two fermions in the same state at the same time. So this is superspace. And you can try to play the same game. You have this doubly graded representation of Sn. You mod out by the boring part. And what you get is something I'll call the superspace coinvariant ring. And there's a conjecture that was kind of made by a whole bunch of people in Toronto. I call it the Fields conjecture. Nantal Bergeron, Machacek, Zabraki, Mike Zabraki played a big role here. That says that, well, as an ungraded representation, what combinatorial objects do we get? Well, it's not permutations, it's not parking functions, but now it's ordered set partitions. And sorry, there should have been a direct sum over K there. All possible ordered set partitions of n tensor the sign representation. And as a bigraded Sn module, I can write down the doubly graded Frobenius image. So it's going to involve two grading trackers, Q for commutative grading, Z for anti-commutative grading. And what you get is something that looks like this. You know, it's a little bit of noise. You know, you have this anti-commutative tracker here, and you have something that morally is a little bit like Lustig-Stanley. It's a sum over standard Young tableau. And you have a Q binomial, you have like major index number of descent showing up, and you have a Schur function corresponding to the conjugate shape of the tableau there. And you can sort of write this in a different way, a little bit cleaner in a sense. This graded Frobenius is, well, a sum where you have your anti-commutative tracker and now something called a delta operator. These were introduced by Haiman, Garcia, and Francois Bergeron. So this is a delta operator applied to En. So this would be a polynomial in your infinitely many x variables with two additional parameters, Q and T, and you zero out T. So this is the same delta operator that appears in the Haglund-Rimmel-Wilson delta conjecture. So this is a conjecture, and it's a really, really frustrating conjecture. It's been frustrating me for over a year now. Let me try to explain why it's frustrating. So we're trying to show that a certain doubly graded representation of Sn has a certain isomorphism type. But here's the thing: with Jim Haglund and Mark Shimizono, I came up with a graded ring Rnk with this definition. I've been haranguing a lot of you about this over the years, and Rnk, basically has the same isomorphism type. We have this delta prime operator here, except we have a little twist, an omega and a q reversal. So we have a ring. Can we just make it agree with the other ring? Maybe we can't. Okay, so maybe you like geometry. So with Brendon Pulowski, I came up with this, this variety of spanning line configurations. So this x and k, it's a certain it's a risky open subset of a product of projective spaces. It's the collection of n tuples of lines in k-1 dimensional projective space, where these lines have to span c to the k if they work together. And we proved that, well, this carries an action of Sn that induces an action on cohomology. The graded Frobenius image of that cohomology representation, well, again, it's this thing with the little twist, right? So maybe you can use geometry. Well, can't do that yet. And maybe you didn't like the little twist. Maybe you can try to get rid of that. So with Andy Wilson, we did this thing. There's a lot of noise here, I'm sorry. But we did this thing where we defined something called a superspace Vandermonde. So we basically took this kind of monomial-like element in superspace. So think of this as a generalized staircase. Like you can define a Vandermonde determinant by anti-symmetrizing over a staircase monomial. So we have something like a staircase that's starting at 0 and going up to k-1, but then it plateaus. And I also have these anti-commuting variables over here, right? And I anti-symmetrize. And, it's this trick which is very reminiscent of kind of classical harmonic theory, where you take this object, you close under all possible partial derivative operators in the x variables, and you take the linear closure. And we can show that this graded module, it's actually precisely this thing. We got rid of the twist, and it's even in superspace, but we still can't prove this conjecture. So this conjecture is really frustrating. It would be great if we could have a proof. So, I hope I've kind of motivated, you might want to consider both commuting and anti-commuting variables. So what if we had like R sets of bosonic or commuting variables and S sets of fermionic variables? What would happen then? So if I don't have any variables at all, we have the ground field. I guess that's kind of an exercise for the reader. If we have one set of commuting variables, we get the classical coinvariant algebra, a very interesting object. In a sense, that's where like classical Schubert theory happens. Two sets of commuting variables, that's the Garcia-Haiman story or Carlson-Mellett story, these diagonal coinvariants. More than two sets of variables, Francois Bergeron has a very interesting program where he's looking at these multi-diagonal coinvariants and saying that you can actually get information on these objects by looking at them as GLK cross Sn representations, and you can even sort of restrict to get information about the case where you have two sets of variables. So if I have only one set of anti-commuting variables, I'm again leaving that as an exercise for the reader. It's, you have to work it out, but it's not so bad. If I have one set of commuting, one set of anti-commuting, these are the superspace coinvariants. That's the frustrating conjecture. Yeah, Sam is referencing Mike Zabrocki's blog post. It's an excellent blog post. And here's Mike Zabrocki's conjecture. So Mike Zabrocki conjectured that if I have two sets of commuting variables and one set of anti-commuting variables, that will actually give a representation theoretic model for the Haglund-Dremel-Wilson delta conjecture. So unspecialized to t equals 0. And I should also mention with Andy Wilson, there's kind of an alternative model for this thing involving, again, those superspace Vandermondes that you saw before. And finally, this is sort of the object of study. I've been trying to motivate it. So what if we had no commuting variables at all, but two sets of anti-commuting, two sets of fermionic variables? So I'm calling this the FDR quotient. It's, you've got two kinds of anti-commuting variables, capital theta and capital C, and you mod out by these invariants. It's a doubly graded Sn module. And there's this kind of here, there be dragon space over here. And I should mention that Francois has some very interesting conjectures kind of tying what would happen if you could somehow extend this horizontal line out to infinity to what would happen if you would extend this vertical thing out off to infinity too.
Actually, Brendon,
Yes.
it extends for all pairs of whatever number of commuting and whatever number of anti-commuting you have. So it fills all of the tableau.
Flip across the diagonal. That's very interesting. Yeah.
No, but you can use platistic calculation to obtain everything.
Yeah.
Both RS.
In principle, yeah.
No, very effective.
Well, conjecturally, I should say conjecturally. So what do these things look like? You know, so here's the case n equals 4. I have this doubly graded SN module, the FDR4 ring. And I've drawn you a matrix picture of its doubly graded isomorphism type expressed as a symmetric function. So these modules kind of live in triangles. I have a C degree going up and down and theta degree going left to right. And, you know, we sort of see the ground field in degree 0. That's the trivial representation. And we have these other objects appearing throughout the matrix. So the first question you might have about this is what's the vector space dimension? So the dimension here is a binomial coefficient, 2n minus 1 choose n. This was conjectured by Mike Zabrocki in the blog post that Sam mentioned in the chat. If you want to get more refined information, you might wonder what the sign and trivial components are. So there's a unique trivial component in bi degree 0, 0. That's this S4 up here, right? And that kind of makes sense because we're modding out by, you know, the invariance with vanishing constant terms. We're killing off the other trivial pieces. You can also see we have this diagonal axis of symmetry. That makes sense because we're treating the theta and c variables in the same way. And if you're interested in the sign representation, that's the S1111 here. You'll kind of notice that there's one copy along each diagonal component, and that always happens, right? So the bigraded multiplicity of sign is this QT analog of n. And furthermore, there's a formula that I didn't write down that tells you what the bigraded multiplicity of the hooks are, right? That's also nice. And what's the full bigraded isomorphism type? Well, we can express this too. So if I fix a bi degree I and j, well, this ring only exists inside the triangle. Yes, Teddy, both the c and the theta are fermionic. That's absolutely right. So this has to live in a triangle. So this will be non-zero if and only if I plus j is less than n. And if I plus j is less than n, the graded Frobenius image here is going to be this Kronecker product of hooks minus this Kronecker product of hooks. So it's a difference of Kronecker products of hooks. And you can evaluate that using the work of Mercedes Rosas. I believe that was her PhD thesis at Brandeis. Or the work of Blasiak, or the work of Liu. So you might also wonder, well, what's the bigraded Hilbert series? So this is coarser information. I'm just telling you the bigraded dimension. So this is the FDR4 ring. And if you look along the diagonal, you see 1, 6, 6, and 1. So 1 plus 6 plus 6 plus 1 is 14. And hopefully people listening to this talk will have an immediate reaction to that. That's a Catalan number. That's the fourth Catalan number. And 1 plus 6 plus 6 plus 1, that maybe takes a second longer, but those are in fact the Neriana numbers, these numbers that, that refine the Catalan numbers. And yes, Teddy, it is true in general. Thank you for setting me up. So if k is between 1 and n, if we're marching along this diagonal, the dimension of the associated diagonal component is this kth Neriana number. If you haven't seen these before, they're given by this kind of a product. And therefore, the sum of the dimensions is the Catalan number. So what we have here, if we look at the diagonal, is a Catalan into Neriana graded SN module. And you might wonder, well, what is this module, right? Can we describe it combinatorially? Is there an action of SL2? Yes, there is. So how do we think about this thing combinatorially? So there are many Catalan objects out there, hundreds, many of which decompose nicely into Neriana objects, but the point of view I'm going to take is non-crossing partitions. So here is a non-crossing partition of 1, 2, 3, 4, 5, 6. The idea is that these blocks do not cross. And here is a partition that is not non-crossing. It is a crossing partition of 1, 2, 3, 4, 5, 6. So there are Catalan many non-crossing partitions of the numbers between 1 and n, and there are Neriana many of these partitions that happen to have k blocks. So I'm going to let NC of nk be the family of non-crossing partitions of the numbers between 1 and n into k blocks. And V and K, well, there's a way to turn a set into a vector space, right? Just take the collection of formal linear combinations of these objects. So the dimension is automatically correct. It's the Neriana number. And the problem now is how do we get Sn to act on this set? So there's a natural action of Sn on set partitions, right? You just kind of permute the indices, but the problem is that this certainly does not preserve the non-crossing property. Like, there's a permutation that takes this to this. So how do we fix this up? So here we come to the following definition. So this was actually made I came up with it a few years ago in the context of the cyclic sieving phenomenon. I was trying to get a representation, theoretic interpretation of cyclic sieving results of Reiner, Stanton, White, and also Oliver Pechenik. So, what's going on here? There's a little bit of noise, sorry. But if I have a set partition pi in NC of nk, and if I have an index I between 1 and n, well, I'll tell you how to apply the adjacent transposition SI to pi. So, there are a few cases here. I mean, like if both things were singletons or I and I plus 1 were in the same block of pi, you just formally negate pi. If just 1 is a singleton, you swap I and I plus 1 in pi. That's what this SI in parenthesis means. But if neither I and I plus 1 are singletons, you're going to introduce a crossing when you try to move these blocks past each other. So that crossing has to be resolved. And the way you resolve it is with these skein relations. So that this top skein relation, if you've studied things like temporally Lie algebras, you've seen it before. It's this thing that says that if I have a crossing like this, you resolve it in 2 different ways and you add. These lower 2 skein relations, are a little bit less classical, and I'd be curious to see what they mean. So here there are supposed to be at least 2 blue dots and at least 2 green dots. So if I kind of cross a 2 block with a bigger than 2 block, I have these 3 terms with some interesting signs. And if I cross 2 bigger than 2 blocks, I get 4 terms with some interesting signs. So I'm calling this sigma map the skein map. It's resolving skein relations. So the fact here is that this actually gives a well-defined action of Sn on V and K. So this map respects the Coxeter relations. And furthermore, what you have is an isomorphism between V and K and this diagonal component of the FDR ring. Okay. So fermions and non-crossing partitions might be interesting to have a sort of deeper connection there. So let's talk about sort of the world beyond type A. So I'm going to let W be an irreducible complex reflection group acting on its reflection representation V. So I can cook up a whole bunch of modules from this story. So W is, of course, acting on V, but it's also acting on the dual space, V dual, of linear functions from V to C. And of course, it acts on the direct sum of V and V dual. And it acts on the exterior algebra over the direct sum V dual. So this will be a doubly graded, right? SN or W module, sorry. One grading coming from V and one grading coming from V dual. And this is the thing playing the role of C brackets theta and Cn.
So Brendon?
Yes.
Just a short another question from Teddy.
Yeah.
So do you have anything to say about other diagonals? Maybe
Other diagonals, well,
anti-diagonals.
kk instead of n minus kk, kn minus k. Not that I'm aware of. There might be something interesting there if you just look at these hook Kronecker differences.
Okay.
Okay. So we do basically the same thing. We take now the W invariance with vanishing constant term, and we have this bigraded representation now of W. And what are the results here? So the interesting thing is that the structure of this quotient, in a sense, it's not so sensitive to W, right? It's sensitive to the rank of W. So if W has rank n, so the symmetric group would have rank n minus 1, the dimension of this FDR space is always a binomial coefficient, 2n plus 1 choose n. And also this ring lives in a triangle. So if I plus j is bigger than n, the ij graded piece is 0. And if I plus j is less than or equal to n, so what's the analog of a difference of Kronecker products of Hookshires? Well, it's a formula that holds inside the representation ring of V. So that's this ring where like addition corresponds to direct sum and multiplication corresponds to Kronecker product or tensor product. So what I see is this formula where I have exterior powers of V, the reflection representation. So think of those as hooks, or exterior powers of V dual. So in Sn, that makes no difference, but for other reflection groups, it might. And I have a difference that looks something like this inside the representation ring. So again, something that we can define sort of with total clarity. So I'd like to talk about just a little bit of the technology that was involved with the proofs. And a lot of people are here. This is one of the largest audiences I've ever had, and a lot of people that know a lot more geometry than I do are here. And it would be great to see if there's a geometric interpretation of somehow what's going on here. So I want to talk a little bit about Lefschetz theory. So we're going to think about a graded C algebra A that lives in dimensions 0 through n. So it's going to be called a Poincare duality algebra if first off an, the top graded piece, is isomorphic to C, and secondly, if I apply the multiplication map between complementary graded components, we're going to get a perfect pairing. Oh, Sheila, yeah, you can see, I don't think that was known before. I mean, you can actually compute that is a genuine character using the Rhoades formula, but I don't know that anyone had done that. So it's possible, but. So anyway, if this thing is a perfect pairing, which would in particular imply that the Hilbert series of this algebra is palindromic, this is called a Poincare duality algebra. And a Poincare duality algebra satisfies something called the hard Lefschetz property if I can find some element L in A1, such that when I am in these complementary degrees, if I multiply by the appropriate power of L to go between them, what I get is actually a linear isomorphism. And this element L is called a Lefschetz element, or technically a strong Lefschetz element. So Lefschetz elements classically arise in geometry. So if X is a nice space, so say a smooth, compact, complex manifold, its cohomology ring is a Poincare duality algebra which satisfies the hard Lefschetz property, at least after you fix the grading up a little bit. So one example of this that's relevant to us is if I had the Lag manifold, the cohomology ring is this coinvariant algebra. So this satisfies hard Lefschetz. And in fact, you can show that, well, what's an element of degree 1? It's just a linear form that looks like this, a1x1 plus a2x through a and x. And this will be a Lefschetz element if and only if these coefficients are distinct, right? So all the coefficients have to be different. It's somehow a regular element under the action of Sn. That's what it means to be Lefschetz here. So let's make this a little bit more combinatorial. I'm going to talk about the Boolean coset. So we're going to think about an integer n and some number k that's no more than half n. So as you all know, n choose k is equal to n choose n minus k. So we can define a square matrix where I guess the columns are indexed by k element subsets and the rows are indexed by n minus k element subsets. And the rule is you put a 1 if and only if you have containment, and you put a 0 otherwise, right? So here's a picture of this matrix M41. And well, maybe linear algebra students can show that this matrix is invertible. It's a little iffy, this 4×4. But Hara and Watanabe proved that, in fact, this matrix is always invertible. So this is always an invertible matrix. And in fact, Hara and Watanabe were thinking about this in the context of Lefschetz theory. So they weren't thinking about the flag manifold anymore, but they were thinking about this other space where I take the Riemann sphere and I take the self product of it with itself in times. So its cohomology ring can be presented like this. It's a polynomial ring in variables modulo the squares of these variables. And here somehow the ith variable corresponds to this ith tautological line bundle over the ith copy of pi or its dual. And what they showed kind of using this theorem is that the sum of the variables, x1 plus x2 up to xn, is a Lefschetz element inside this thing. And if you're studying representation theory, this is kind of good news because this guy is Sn equivariant, right? This is a symmetric polynomial, whereas in the flag manifold case, to be Lefschetz, you were the opposite of symmetric, right? You were actually changed by any permutation, right? So we have access to, in this setting, equivariant Lefschetz elements. Now, what do I mean when I say exterior Lefschetz theory or fermionic Lefschetz theory? So we'll take our polynomial ring in 2n fermionic variables, theta n and cn. It's now a bigraded ring. We have a direct sum over I and j of the ij piece going from 0 to n. And we can observe something that looks a little bit like Poincare duality, right? When k is 0, it's a 1×1 matrix of 1. That's invertible.
Brendon, would you mind repeating the questions when they come up in the chat, just in case people are in the future watching this without the chat at hand?
Certainly. Thank you. Right, so Teddy was asking if this matrix was invertible when k is 0. It's a 1×1 matrix with a single entry 1 in that case. So, right, so this ring satisfies a bigraded version of Poincare duality, right? This top bi-degree piece is, of course, isomorphic to C. It's a one-dimensional complex vector space. And furthermore, if I kind of multiply between two complementary bidegrees, what I get is a perfect pairing, right? Sorry, shouldn't have been isomorphism, should have been perfect pairing. So this is a bigraded Poincare duality algebra. And what about Lefschetz theory? So this was really kind of the results on which all of our proofs hinged, right? So what can play the role of a Lefschetz element here? Well, we're going to look at the following special element of these, I guess this fermionic ring. It's going to be theta 1 c1 plus theta 2 c2 up to theta n cn. So again, this is something that is equivariant. And if I plus j is less than or equal to n, you can set R to be n minus I minus j. And what Jongwon and I showed, kind of building on the Hara Watanabe results, is that if you look at this ij graded piece where I and j aren't too big, and if you multiply by the appropriate power of delta to land in its kind of friend piece, n minus j, n minus I, this map is a linear isomorphism, right? So you can use the result of Steinberg to show that the relevant ideal that you mod out by for the FDRW ring is principal, generated by delta n. And then you can use this trick, which was used to great effect by Richard Stanley, that says that if I have a given power of delta affording an isomorphism, the first application of delta had to be injective and the last application of delta had to be surjective, right? And the W equivariance of delta somehow finishes the proof. But what I'd love to ask is there some kind of a geometric meaning here? I mean, this is a version of Lefschetz theory that, we used for representation theoretic purposes, but it's applying to these fermionic rings. And I'd love to see a geometric interpretation. And with that, I'd like to thank everyone for listening to my talk.
Thank you. Let's all share reaction
Should I stop
for
sharing
this
now?
great talk. And I think I'll hand it over to Peter.
Yes, let me get my. So I don't see any questions.
I have one.
You have a question? I know Sam has a question now. Could you state it yourself?
Are you inviting Sam or me?
Samuel?
Okay, yeah, really great talk, Brendon. So I'm interested in that symmetric group action on non-crossing set partitions, which you described.
Yeah.
So you mentioned it's very similar to the kind of action on non-crossing matchings, like the Temperley-Lieb style thing. Do you so in that situation for the non-crossing matchings, that action can be realized as a symmetric group action on invariant tensors of tensor powers of, I think, vector representation of SL2 or something like that. Have you thought about if your non-crossing set partitions action is like an invariant tensor action for some kind of Lie algebra representation?
That's a great question. So when I wrote down a similar version of this thing kind of a few years ago in the context of cyclic sieving, that's something I was wondering about. I couldn't quite prove it. So one hint might be those representations are somehow built out of flag-shaped representations. So these are corresponding to partitions of the form KK 1 1 1 1 1 1 1. You know, I think you want to start with these flag-shaped guys and try to get an invariant theoretic interpretation of those. That's where I'd start.
Great. So if you have questions, maybe raise your hand. But I see there are some questions in the chat.
Another question. Going back to my question before, is there an actual injection between the modules, the difference of Kronecker products?
Oh, well, yes, it's afforded by delta, by this Lefschetz element. So the Kronecker product, think of it as like you have your hooks, which are like if you just had one set of fermionic variables modulo the sum of the variables, you get hooks. So the Kronecker product is two sets of fermionic variables. So your Lefschetz element is telling me that when I multiply, because my ideal is principal by work of Steinberg, you know, that's what's going to happen. You're going to be subtracting off the smaller piece.
Okay, thank you.
Okay.
So Jim has a question.
Yeah. So do you and Jongwon also get a monomial basis for the diagonal fermionic coinvariant ring?
Yeah. So if you look at the FDRW rings, you get a monomial basis that's indexed by lattice paths that are somewhat similar to Motzkin paths, except they don't have to actually end on the x-axis, and their horizontal steps kind of come in one of two decorations. If you look at the FDR in-ring, there's a slight complication because you mod up by the variable sums. So we do actually get a basis. These are paths that are kind of like Motzkin paths, but they have to stay strictly above the x-axis. I think those are Schroeder paths. So you know, there is a basis. It's not monomial though.
Oh, okay.
Cool. And Vic, you have a question?
Yeah, great talk, Brendon. Can you tell us, what do you know in the case when W is not the symmetric group about the action on that diagonal that's at the top of the coinvariants?
That's an excellent question. I haven't looked into it so much. I mean, the strange thing, right, is that it's always the type A Catalans and Arianas. It's not like it's the type W, right, Catalans and Arianas that you're getting. So, you know, I at this point, I could just say it's a certain difference of exterior powers, you know, of like V and V dual, but it would be interesting to see if you could even get a combinatorial model for this thing in other types.
Thanks.
Okay, I have a question. Brendon?
Hi, Teddy.
In your slide, the penultimate page, just before, you don't have to go back,
Okay.
You define delta to be the product of the sum of theta 1, xc1, theta 2, xc2, blah, blah. Wouldn't your argument possibly hold if you change this product into theta 1, cn, and reverse it, you know?
Yeah, you can take you could do the x's first or the thetas first. It would have been the same thing. Yeah, you would also have that same Lefschetz-like property.
And you mentioned also the Motzkin paths in your 2 minutes ago. And where does the fermionic variables reflect? How do they reflect on the Motzkin paths? Like,
well,
theta 2 squared, theta 1 squared is 0, and so on, right?
So what happens there, I mean, you can look at the paper, but what's going on is you look at the FDR-W ring, that's actually the easiest way to state it, then you're modding out by a principal ideal, and if you use the version of Grosvenor theory, so there's a version of Grosvenor theory that applies to anti-commuting variables, and the standard monomial basis, when you work it out, ends up giving you these paths.
Thank you.
And Yuval, you have a question?
Yuval said that he doesn't have a microphone.
He doesn't have a mic.
Ah, okay. So let me read it out. So is there an analog for other types? For example, graded actions on their NC, and then I don't.
Well, you know,
analogs.
So I would say that's kind of tied in with Vic's question. I mean, in a sense, you know, the vector space dimension of these diagonal pieces is kind of insensitive to the group W. It only cares about its rank, and it's always these type A Catalan and Marianas. So yes, there is an action of W coming from this fermionic theory for any W, right? But, you know, how do we understand this action of like type W on type A? That's, I don't know how to do that. It's a good question, Yuval, though.
And maybe we have time for one other question. So Francois?
Yes. By the way, I just put up the general formula, how you can get for many set of commuting and many set of non-commuting from the general diagonal convariant. Anyway, did you look at more sets of anti-commuting variables for the Coxeter group? This has to become stable, but it must have this kind of similar property.
I looked at this somewhat. There are computational issues, right? Because every time you throw in a new set of variables, so, you know, the unfortunate thing is the most naive thing you would be hoping for, where you have kind of these multiple Lefschetz elements indexed by subsets of variables, and you would just subtract off hook chronikers. That doesn't work. You actually get things that are not sure positive. So I'm not really sure how you would analyze that algebraically at this point. I'll have to kind of think harder about that. But I don't have so much computational data, and it would be interesting to see how it meshes with your work.
Yeah, great, very, very good talk. I enjoyed it a lot. So thank you.
And Sarah, did you have a question? I saw you raised your hand, I think.
I do, and I put it in the chat, but why don't I talk with you after, in the coffee time? I'll ask my question, because it's time for us to move on to the next talk. Yeah. This was very good, very nice talk.
Maybe we'll take 2 minutes and set everything for Philippe. Yeah. So let's thank Brendon again. Thank you.